And the recording is live. Okay. Okay. Over the next 2 lectures, we're going to be covering reactions. And within reactions has a lot of subtopics. So I kind of wanted to make those subtopics clear from now. That way we understand exactly the bird's eye view of this topic as a whole. Under reactions, one of the first things we're going to uncover is the concept of balancing reactions. We will then cover state symbols. Under state symbols, we will also go over solubility rules. Reaction archetypes. And if we have time today, we will start the concept of predicting products. I don't expect us to be able to get to this particular topic today, but just in case we do, after predicting products, we'll also talk a little bit about ionic equations. So this just gives you an outline of the topics that we're going to be spending a lot of time on over the next 2 lectures and lab on Friday. First one I'd like to start with, of course, is balancing reactions. The concept of balancing reactions comes from one of our most fundamental laws of physics, that matter can neither be created nor destroyed, but merely transformed. In the case of balancing reactions, we will specifically only use whole numbers. And the big idea is that we want there to be consistency. In other words, we want our reaction to show evidence that nothing has been created nor destroyed, but rather transformed. Let's take a very sample generic reaction. Shown here, we have the reaction between copper sulfide plus hydrogen chloride to give us copper chloride and hydrogen dihydrogen sulfide. We don't know fully yet what this exactly means. All we know is left and right. So let's talk a little bit about that. Over here on the left side, it is sometimes referred to as the left side. These are what are known as your reactants. On the right-hand side, again, sometimes actually called right side, these are what are known as products. Let's try to understand when to identify if a reaction is not balanced, and of course, how to do it. So the process is simple. We will normally go from left to right. We're going to work from left to right. We're going to start with copper. We can see that there is only 1 copper on the left. We see that there is 1 copper on the right. We can make an effort to write that down. We have 1 copper on the left, 1 copper on the right. After copper comes sulfur. We can see that on the left-hand side, there is only 1 sulfur. On the right-hand side, there is only 1 sulfur. So we make a note of that. 1 copper, 1 sulfur on both sides. Next, we have hydrogen. We can see that there is only 1 hydrogen present on the left-hand side. But this is in stark contrast to the product side. We see here more specifically that there are 2 hydrogens. Keeping it going, all we have left is the chlorine. We can see on the left, there is only 1 chlorine. However, like the hydrogen, there are 2 chlorines on the right. By the law of conservation of matter, copper and sulfur is neither created nor destroyed, merely transformed. There is one copper, one sulfur on both sides. Both copper and sulfur are balanced. However, looking at the hydrogen and the chlorine, we can immediately see that these are not balanced. There is only one of hydrogen and chlorine on the left, and there's two on the right of each. This is unbalanced. This is something we need to fix/balance. So again, going from left to right, we're going to go one element at a time. Copper is already balanced, so check on that. Sulfur is also already balanced, check on that. And right now we're dealing with the hydrogen. To balance this, we simply put a 2 in front of the HCl. The reason why we put the 2 in front versus something like H2Cl is because H2Cl simply does not make sense as a formula. We know, of course, that hydrogen in group 1, chlorine in group 17, these should lead to a 1-to-1 ratio. So we would never, when balancing, we're not going to put those small subscript numbers. They're going to be big numbers in front. In doing so, I have now balanced the hydrogens. So just to go over it one more time, copper is fine, sulfur is fine, hydrogen is now fine. All right, moving on. Next up, we have chlorine. Now, here's where that big number in front becomes pertinent. We are saying there are 2 HCl's, which means in total, there is an HCl here and an HCl there. We have in total 2 chlorines now. That's, of course, different from what we had earlier. No big deal. We'll just update it. And by the sweet serendipitous of it all, we recognize now the chlorine is already balanced. It was not on purpose, but it worked out that way. So this is one of the first lessons of balancing. As you work through the reaction methodically from left to right, don't be surprised if by the time you finish, everything is balanced without you having to do all of the chemicals. Let's try another one. This is the reaction between H3PO4 added to NaCl gives us Na3PO4 plus HCl. At this moment, you do not know how I got the products. We're not there yet. All we're focused on right now is balancing, numbers, counting. As you do more and more practice of these types of questions, you'll be able to start balancing these reactions in your head. That's, of course, the ideal outcome by the end of the semester. But right now, in the beginning, we're still learning. I do recommend you take the very tedious route and outright label each ion. We have a hydrogen, we have a PO4, we have a sodium, we have a chlorine, and all of these are also on the product side. Right now, we can see that there are 3 hydrogens on the left, 1 phosphate, 1 entire phosphate ion on the left, 1 sodium, and 1 chlorine. On the right-hand side, we see that there is 1 hydrogen, 1 phosphate, 3 sodiums, and 1 chlorine. I want you all to notice something. Notice that when I talk about balancing, I grouped the entire PO4 together. I did not specifically break it up into 1 phosphorus and 4 oxygens. The reason why we do that is because phosphate is a polyatomic ion, so it is considered a single ion, its whole group. By that same code of logic, it should make sense why I did not automatically carry over the 3 for the hydrogen, or why the 3 of the sodium did not exist in the first place. Remember that these subscript numbers represent the crisscross. For example, with H plus and PO4, which is 3 minus, crisscross tells us there will be 3 hydrogens and 1 phosphate. Similarly, sodium plus and phosphate 3 minus, the same idea. 3 gets carried down and there's only 1 phosphate. So the big takeaway from this is the only time these subscript numbers will automatically carry over or be grouped together like this is only when it's a polyatomic ion. This is why it's important that we start memorizing, if we haven't yet or haven't gotten it under pat, what our polyatomic ions are. But that's just a small tangent. Let's go into balancing. Normally, we will work from left to right. Starting with hydrogen, we see that there are 3 hydrogens on the left and only 1 hydrogen on the right. No big deal. To balance it, we'll put a 3 on the right. In doing so, we have now balanced the hydrogen, but we have also done something else unintentionally. By putting the 3 in front of the HCl, not only are we saying there are 3 hydrogens, we are also saying there are 3 chlorines. So now that must be updated. Keep me going from left to right. Hydrogen is now balanced. Phosphate, there's only 1 of, so that's balanced. Next up, we have sodium. We have 1 sodium on the left. We see we have 3 sodiums on the right. To balance this, we will simply put a 3 in front of the sodium chloride. In doing so, we now have 3 sodiums balanced. And let's keep it going. After the sodium, we have in total 3 chlorines. Oh, would you look at that? We also have 3 chlorines on the right. So again, as I pointed out, as you balance this methodically, don't be surprised if by the time you finish, everything is balanced for you. Notice we did not particularly set out to balance the chlorine. It's just that by the time we got through all the others, chlorine was also balanced. So this topic is the kind of topic where you need to trust the end game. You need to trust that everything is going to work out. If it doesn't, that means that you're wrong and probably need to start over. That's balancing chemical equations. After that, we're now going to talk about state symbols and solubility rules. Solubility. Okay. Now, the term state symbols quite literally mean what it says. We have various states. We have solids. We have liquids. And we have gases. These are the 3 states of matter that we've already covered in this class. Now we just need to know their symbols. Pretty straightforward. Solids have the symbol bracketed S, S for solid. Liquids have the symbol L, L for liquid. And gases, to no one's surprise, is G. G is in gas. Now, identifying the states of different chemical compounds comes back to the periodic table. We know something is a solid if on the periodic table it's a metal or, of course, a transition metal. When it comes to gases, we know some gases already. These include the diatomic elements such as H2, N2, O2, F2, etc. There's also some that you may know, that may not immediately recall, specifically CO2, carbon dioxide. So how do we know what our gas is? Well, to be quite honest, it's a matter of remembering or knowing them off the top of your head. There's not that many. The newest state that we are introducing is referred to as aqueous. You might hear some people pronounce it aqueous. I don't think there's a general consensus on what the pronunciation is. Aqueous. This is given the symbol AQ. AQ for aqueous. Now, to understand exactly what aqueous means as a state, we must note that most reactions, especially the ones we're only going to see in Chem 300, most reactions, that's over around 95% of them, take place in water. So the term aqueous quite literally refers to dissolvable. An example of this is sodium chloride. Now, sodium chloride, we all might affectionately know this as table salt. We know for a fact that table salt is a solid. We can see it, we can buy it, there's no doubt about it. But we also know that table salt is dissolvable in water. For that reason, it is given the state symbol AQ. Compare that to something like magnesium, a strip of magnesium metal. If you were to drop that magnesium metal in a cup of water, would that magnesium strip dissolve? No. So magnesium is classified as a solid. So the term aqueous simply means dissolvable in water. Since water takes up such an important part of this chemistry, this reactions, water is not defined as aqueous because water can't be dissolved in water. Water is given the state symbol L as in liquid. In fact, it might be the only liquid we encounter in this class because, again, most reactions take place in water. So there are only very few liquids. Water is one of them. Gases, that's on you to recall your diatomic elements. Solids, you can look at the periodic table to identify if something's a metal or not. The only question is right now, how do we determine if something is aqueous? Because table salt is one thing. Most of us are familiar with table salt. But you can't use that logic every single time because, well, you may not know every single chemical we encounter. So how do we tell the difference between a solid compound versus an aqueous compound? This is where solubility rules come in. That handout that was given to you on the first page is our table of solubility rules. Now I'm going to make something clear. You will be given this table as part of the exam booklet. You will be given this table as part of the exam. It's going to be a reference sheet, just like the periodic table. So you do not need to memorize this table, but you do need to know how to use it. Similarly, since I have the opportunity, I'd like to point something out. On the other side of that handout, is a table that summarizes all of the reactions we are going to cover this week. This table is not one I expect you to memorize. It is simply a summary of all of the reactions we're going to cover this week. So this part, the back part, is really just for your own knowledge and studying. But the first page is something you will be given on an exam that I do expect you to know how to read and understand and manipulate. So let's try it. Let's start with an easy one. Let's go back to one of the reactions we just did. Let's go back to this H3PO4 reaction. We just did it. We just balanced it. Let's now incorporate state symbols and understand how to read this. The table is meant to be read in the direction of its columns, one at a time. If the compound contains a chlorine, then it is soluble except when bonded to. So it's very much meant to be read as a full, complete sentence. So let's use that and try to identify whether or not the following compounds are aqueous or solid. From left to right, we start with H3PO4. We see a PO4 as part of the formula, and we also see PO4 on the sheet. You have the hard copy in front of you. So let's read it. If the compound contains a phosphate, then it is solid, except when bonded to a group 1 cation. And guess which group hydrogen is in? Group 1. So for H3PO4, would I write S or AQ? AQ. It is written as a small subscript bracket right beside the number 4, so it doesn't take up too much space. I don't want to see a big whole capital letter, big size, the same size of the formula. It should be subscript. I, of course, deduce this using the PO4. But you also could have deduced the answer by looking at the hydrogen. If the compound contains a group 1 cation, then it is soluble, no exceptions. So whichever perspective you used, you would arrive at the same answer, aqueous. Let's keep going. We already know that sodium chloride is aqueous. That was one of our examples, but let's just see it for ourselves. Chlorine, if the compound contains a chlorine, then it is soluble, except when bonded to silver or lead. Is this an exception? No. So this is aqueous. Again, that was just one perspective. We used the chlorine. What if we looked at the sodium? Sodium is in group 1. So if the compound contains a group 1 cation, then it is soluble, no exceptions. Two paths lead you to the same destination. Keeping it going over here on the right-hand side, again, we have sodium and phosphate. Sodium, compound contains a group 1 cation, aqueous, no exceptions. I'm not even going to look at the phosphate. HCl, yet again, we have a group 1 cation. It is soluble, no exceptions. Here again, I know that the HCl is aqueous. So in this reaction, it just happens to be that all of them are aqueous. There's no significance behind it. There's no rationale. We just analyzed each one and deduced that they were all aqueous. Let's try another one. Let's try the copper reaction that we balanced in the very beginning. Copper sulfide plus 2HCl gives us copper chloride plus H2S. I want to be closer to the table, so I'm just going to move this stuff around. That way I don't need to zoom out too much. All right, working from left to right. Sulfur. If the compound contains a sulfide, then it is solid. Is copper an exception? No. Copper is not on that exceptions list. That means that copper sulfide is solid. HCl, if the compound contains a group 1 cation, soluble, no exceptions, aqueous. Copper chloride, if the compound contains a chlorine, then it is aqueous. Is copper an exception? No. So this one is aqueous. Then we have H2S. The compound contains a group 1 cation. Soluble, no exceptions. Aqueous. So here, in this case, at least one of them is a solid, the copper sulfide. And the only way we know that, or we knew that, was by going through the table and answering that question. So again, I'll state, you do not need to memorize this table. It will be provided to you on the exam. You just need to know how to use it. Do we have any questions so far? Fantastic. All right, so that takes care of balancing reactions, state symbols, and solubility rules. The next one we are going to cover is, of course, reaction archetypes. Reaction archetypes are just broad classifications of reactions that ultimately help us predict products. One of the first ones we will cover is known as synthesis. Synthesis describes a reaction where two or more chemicals combine into one. This can be generically represented by A plus X is equal to AX. Two chemicals just come together and combine into one. A and X are just meant to represent generic ions and elements. There is no element on the table that's just A or just X. So these are just generic elements. A popular example of synthesis is the combination of sodium plus chlorine to give us sodium chloride. Do remember that chlorine is a diatomic element, so it's actually Cl2. Is this reaction balanced as written? No. Immediately we notice the chlorines are off. No problem, let's deal with that right now. There's two chlorines on the left, one on the right. Easy fix, just put a 2 over there. Chlorines are now balanced, but what did I do? Now I have two sodiums on the right, but only one on the left. No big deal. Let's put a 2 on the right, on the left. Sodium, a group 1 metal, is a solid. Chlorine, a diatomic element, is a gas. And sodium chloride is aqueous. I'll have you try another one. Using this logic that we just went over, synthesis, please predict the products of the following reaction between hydrogen and chlorine. Be sure to balance the overall equation and include state symbols. So just as we did with sodium and chlorine, I want you to do with hydrogen and chlorine. but balance it and also include state symbols. Take about 2 minutes to attempt that. Take another minute. All right, 12:06 by my count. The product of hydrogen and chlorine coming together is simply HCl. One thing we immediately notice is, of course, as written, it's unbalanced. To balance the hydrogens, we'll simply put a 2 in front of the HCl. In doing so, we balance the hydrogen, and to no one's surprise, we also balance the chlorines. All that's left are the state symbols. Hydrogen and chlorine are both diatomic elements. They're both gases. HCl, if you use the table, will lead you to an aqueous species. Yeah.
Diatomic elements, gases?
All of them are. Yeah. All of the diatomics are gases. Yeah. After synthesis, our next reaction archetype is known as decomposition. Decomposition, as the word suggests, is the exact opposite to synthesis. Whereas synthesis combines two chemicals into one, decomposition involves a single compound breaking up into its individual chemicals. We need not look too far for some classic examples of this. In fact, I just said it's the opposite to synthesis. We saw two examples up here. So the best couple examples of decomposition is the opposite. 2NaCl, aqueous, breaks down into 2Na, solid, plus chlorine gas. Similarly, 2HCl, aqueous, breaks up into hydrogen gas and chlorine gas. Therefore, the generic representation can be seen as AX breaks up into A plus X. These two should be the most intuitive of the bunch. This is very similar to a lot of things we've seen so far. If you recall, when we covered nomenclature, we talked about, for example, what's the molecular formula that results between CO3, 3+, and PO4, 3-, cobalt and phosphate. Of course, we would crisscross, and that leads to cobalt phosphate. This is just simply another way of writing that. Each element comes together to form a compound. In the case of decomposition, that compound then breaks up into its respective pieces. The next one that we will encounter is known as combustion. Combustion is a very specific type of reaction that involves a compound of the formula CXHY, where X and Y can be any whole number. These compounds, CXHY, are referred to as hydrocarbons. For those of you who may be familiar with that term, you've probably heard it when talking about fossil fuels. Hydrocarbons will react with O2 and will always form CO2 gas and liquid water. So when we burn fossil fuels, aka when we burn hydrocarbons, aka when we burn CXHY, they will always form carbon dioxide and water. So in the case of combustion, there really isn't any guesswork as to the products. I could, for example, just write CH4 added to oxygen gives us CO2 plus H2O. No rhyme or reason needed. Why? Because I've recognized that I have a hydrocarbon, CXHY. It reacts with oxygen, so it will always form CO2 and H2O. Of course, this isn't a complete reaction. We need to balance it. We also need state symbols. Let's do state symbols first because that's more straightforward. We all have our tables in front of us. CH4 contains a group 1 cation, aqueous. O2 is diatomic element, that's a gas. And you should already know that CO2 is a gas and water is a liquid. So the state symbols are easy. The state symbols are straightforward here. All that's left is balancing. We see on the left, there is 1 carbon. On the right, there is also 1 carbon. So check. On the left, we see that there are 4 hydrogens. On the right, we see there are 2 hydrogens. To balance that, we'll simply put a 2 on the right. Now, carbon is balanced and hydrogen is balanced. All that's left, of course, is oxygen. There are 2 oxygens on the left, and in total, there are 4 oxygens on the right. Pay attention to that. This is the first time we're seeing them coming from 2 different sources. Oxygen is in both carbon dioxide and water. So the cumulative sum of oxygens on the right is 4. 2 from the CO2 and 2 from the H2O. So to balance it, we'll simply put a 2 in front of the O2. With this, the reaction is balanced with state symbols and correct products. Let's try another one. C2H6 plus oxygen will always give us carbon dioxide gas and liquid water. I don't even need to spend more than 2 seconds thinking about it because I know for a fact hydrocarbons react with oxygen and will always form gas, carbon dioxide, and liquid water. What all that's left, of course, is balancing. On the left, we have 2 carbons. On the right, we have 1. No big deal. Just put a 2 right there. On the left, we have 6 hydrogens. On the right, we have 2. No problem there. Just put a 3 in front of the H2O. With that, both carbon and hydrogen are balanced. All that's left is the oxygen. There are 2 oxygens on the left, and in total, there are 7 oxygens on the right. Check the math on that for yourselves. 2 times 2 is 4. 3 times 1 is 3. 4 plus 3 is 7. But there is no simple whole number that we can multiply 2 by to get 7. When we were up here, we had 2 oxygens and 4, so we just multiplied by 2. But 7 is not a multiple of 2. So you might think, well, what if we just put a fraction? 7 over 2. Technically speaking, 7 over 2 times 2. 2's cancel out. We're left at 7. Recognize this is slightly more complicated sounding because of a fraction. Remember what I said at the very beginning about balancing. We prefer whole numbers. So I would prefer if you did not use fractions. So what we would do at this point is simply say, well, let's bump things up. Let's put a 2 in front of the C2H6. 2 times 2 is 4. Put a 4 in front of the CO2. 2 times 6 is 12. Put a 6 in front of the H2O. We still have 2 oxygens on the left, but now in total, we have 8 plus 6 to give us 14 oxygens on the right. This is a number that's a lot simpler to work with. We just put a 7 in front of the O2. Some of us who are more math inclined may be able to recognize, well, Supreet, if we had just put 7 over 2 times O2, couldn't I have just multiplied the entire thing by 2 to get rid of the fraction? Yeah. But if you're not so math inclined, I don't recommend going the fraction route. Do we have any questions so far? Yeah.
So would you not be allowed to put the same level to else be more than?
So if you put 7 over 2, I would give you half credit. Whole numbers are preferred, but it's not wrong. It's just not convention. So you'd get half credit. Yeah. It also depends on how generous I'm feeling. If like 90% of the class is using fractions, I'll just say, you know what, it's fine. I won't take off any points. But if you're like the only person that did, penalty. All right, I'd like everyone to attempt this question on their own. C3H8 plus O2. As before, please provide the products. Please provide the state symbols. Please provide the correct balancing. So 3 things: products, balancing, state symbols. Take about 2 to 3 minutes to do that, and then we'll go through it together. Okay, one more minute. You're predicting the products, you're balancing, and you're doing state symbols. All right, 12:21 by my watch. So predicting the products is straightforward. This is as hydrocarbons with oxygen. The resulting products will always be gaseous carbon dioxide and liquid water. Of course, all that's left is to balance it, as I've already included state symbols. There are 3 carbons on the left, 1 on the right. Easy fix. Let's put a 3 in front of it. 8 hydrogens on the left, 2 hydrogens on the right. Easy fix. Just put a 4 in front of it. Currently, there are 2 oxygens on the left, and in total, 6 plus 4 to give us 10 oxygens on the right. So to balance it, we put a 5 in front of the O2. Before we move on to our next type of reaction, does anyone have any questions? Okay. Our next big reaction archetype, that was number 3. Yeah, so number 4. Is known as double displacement. The double displacement reaction involves chemical compounds swapping partners. So generically, AB plus CD, where each letter represents an ion, will swap partners such that we end up with AD plus CB. A ends up with D, C ends up with B. Let's see an example of this, which is the reaction between sodium chloride and lithium fluoride. We see here 2 chemical compounds, not elements, compounds. And how do we know they're compounds? Because each of them has at least 2 elements. We can very easily line them up, A, B, C, D, so that we can identify what's what, and use the pattern to predict the products. AD plus CB. A and D end up together. This becomes sodium fluoride. C and B end up together. That results in lithium chloride. Now, I'd like to take a moment right here and point something out. When we swapped and we ended up with AD, well, that makes sense in alphabetical order. A before D. But I did not use that logic for the CB. In other words, BC is not what I wrote on purpose. Let's think about why that is for a second. Over here on the left-hand side, we see that C was written first. So it's presumably the cation. Remember that from nomenclature. The one written first on the left is positive. Similarly, the B in AB is negative. So when they end up together, positive goes in front, negative goes in the back. Using that example right here with lithium chloride, if, for example, you did not remember that and you wrote chlorine lithium, technically speaking, this isn't wrong. I'm just going to put a frowny face right beside your answer. It technically isn't wrong. It just looks really weird to me. So I want to make that part clear about how we organize our ions. Finishing around the curve lets us do our state symbols. Both sodium and lithium are group 1 cations. So they're aqueous with no exceptions. Let's check balancing. 1 sodium, 1 sodium, 1 chlorine, 1 chlorine, 1 lithium, 1 lithium, 1 fluorine, 1 fluorine. So the reaction is balanced as written. Everything is 1, 1, 1, 1. That's double displacement. Let's look at our last one. Single displacement. Both double and single displacement involve, well, displacement. In double, chemical compounds swapped partners. In single displacement, one element replaces another. What does that look like? The generic reaction between A and BC. Compare that to the double displacement up here where we had 2 explicit compounds. In single displacement, we have a compound and an element. This results in AC plus B. As we can see, the single element A replaces B. Let's take a look at an example of this. The reaction between sodium and lithium chloride results in the sodium replacing the lithium, resulting in sodium chloride plus lithium. The element that gets replaced ends up by itself as a neutral element. So here's a good question. How did I know that the sodium would replace the lithium? Why would it not replace the chlorine? Does anyone want to take any guesses? Ryla? That's exactly correct. Sodium is in group 1, so its ideal charge is positive. So if given a choice between the positive lithium and the negative chlorine, it will replace the lithium. Like replaces like. The same thing can actually be said for the opposites. The reaction between Cl2 and sodium fluoride. Here again, we have a situation where an element will replace another. But we should remember that chlorine, which is in group 17, has a charge of -1. So if given a choice between the sodium and the fluoride, which will it replace? The fluoride. So the result here is sodium chloride plus F. I know I'm missing state symbols and balancing, but as written, is there something missing? I know I'm missing state symbols and balancing. We're not there yet. I'm saying beyond that, is there something on this reaction right here that is incorrect? I saw your hand first, Andrew.
Chlorine.
You said chlorine or fluorine? All right, we already have two over here on the left. Are you talking about this one right here? That's balancing. We're not there yet. Otherwise, as written, yeah, I see your hand, Paul.
Chlorine and diatomic.
Fluorine is a diatomic. So it doesn't just end up by itself, it ends up as F2. This is what I mean by this is a big topic that a lot of things start building on themselves. So you have to start keeping track of a lot. Now that that's correct, let's balance it. 2 chlorines, 1 chlorine, no big deal. Just put a 2 on the right. Chlorine is now balanced. 1 sodium, 2 sodium, no big deal. Just put a 2 on the left. Chlorine is balanced, sodium is balanced. And sweet serendipity, fluorine is now balanced. As we've pointed out and seen many times, as you work through the balancing systematically, things tend to work out. All that's left, of course, are the state symbols. We're at the point where we should remember that table salt is aqueous and a diatomic fluorine is a gas. Let's try another one. Let's try zinc solid added to copper sulfate. We're at the point where we recognize zinc is a transition metal, so it most likely will form a cation. That means that it will replace the other transition metal, which is a cation. The result is zinc sulfate plus copper. Now, here's the thing. All the other cases we've worked on so far, such as the sodium chloride, the sodium fluoride, and the lithium chloride, these are all examples of similar charges. So the crisscross tells us this will be 1-to-1. How do we know what the charge is of the zinc in this product? The simple answer is we don't. It's a transition metal. We can't just look at the periodic table. We're pretty confident it's positive. We just don't know if that's +1, +2, or +3, or +4. Here's the logic. Since zinc replaces copper, it makes the most sense that it also replaces the charge. So sulfate is 2-. The fact that copper sulfate is 1-to-1 tells us that copper is +2. So when zinc replaces copper, it also becomes +2. Zinc sulfate is aqueous, copper is solid. 1 zinc, 1 zinc, 1 copper, 1 copper, 1 sulfate, 1 sulfate. You have a question?
Why do we have the charges?
Very good question. You know what? Let's actually answer that right now. Does anyone, I'll answer it with our next topic, but does anyone have any other questions? Our next topic will answer your question. Okay. Single displacement ends our conversation on reaction archetypes. What we need to do now, or the next big thing, is a sample question that says, provide a complete balanced equation with state symbols for the reactions below. You can expect this instruction to be pretty much the exact same on your exam, Provide a complete balanced equation with state symbols. And I'm going to go ahead and tell you that this question is traditionally worth 3 points per reaction. The 3 points come from number 1, the correct products. The second point comes from correct balancing. And the third point comes from the correct state symbols. Just so you understand where the points are coming from. The reaction is sodium chloride aqueous added to barium fluoride, which is aqueous. Now, I will give you exact instructions on how to predict the products here. Step 1. The very first thing we are going to do is we're going to identify the archetype. In this case, we should quickly recognize this is an example of double displacement. This is actually going to be one of our most popular reaction archetypes. Double displacement accounts for, I think, like 85% of all reactions. Once we identify the archetype, we are going to match ions. Then we're going to crisscross as needed. Finally, after crisscross, we will balance the reaction and include state symbols. Okay. We have already identified the archetype. Hopefully, we should recognize this as double displacement. These are two chemical compounds coming together. We're going to use that AB plus CD to give us AD plus CB. Now we're going to match ions. Now, I want to be something absolutely clear. This procedure is meant to be followed in order. More often than not, when I see students making mistakes in reactions, it's because they've gone from number 1, skipped to number 3, ignoring number 2 entirely. But this is meant to be followed in order. Let's see how that looks. The very first thing we're going to do is match ions. A ends up with D. That becomes NaF. Next, C ends up with B. This becomes barium and chlorine. I have simply matched the ions together based on the archetype. Quick check. There is a 2 of the barium fluoride right here on the left that is not present on the right. Does anyone want to take a guess why? Yeah. Well, we're not at crisscross just yet. I'm asking why I didn't automatically put the 2, just as I did with the PO4 in one of our earlier questions. In other words, I'm asking why did we not carry over the subscript number for fluorine? Simple answer is it's not a polyatomic ion. So the 2 is not carried over automatically. Ions are matched. Now we're going to crisscross. As he just pointed out, sodium in group 1 is +1. Fluorine in group 17 is -1. Face values are the same. Crisscross leads to 1-to-1. This is just simply NaF. All right, what about the next part? Barium and chlorine. Barium is in group 2. So it has a 2+ charge. Chlorine in group 17 has a -1 charge. We do have to crisscross, leading to BaCl2. And to answer the earlier student's question, this is why it's important to know the charges. Because if you completely forgot that you have to worry about charges, you would not have the 2 at all. And no matter what, your answer is going to be wrong. All right. We've identified archetype. We've matched ions. We've crisscrossed as needed. Now we're going to balance and include state symbols. We're going to balance first. 1 sodium, 1 sodium. 1 chlorine, 2 chlorines. Okay, no problem with that. We actually just put a 2 in front. In doing so, we have balanced chlorine, but guess what we also did? We messed up sodium. Now there is 2 sodiums on the left, but only 1 on the right. That's not a big deal. Just put a 2 in front. Now the sodium is balanced. The chlorine is balanced. 1 barium on the left, 1 barium on the right. 2 fluorines on the left, 2 fluorines on the right. Would you look at that look? Again and again, I will state it. As you balance methodically, don't be surprised if by the end you've balanced everything without trying. Now that we've balanced, all that's left are state symbols. Sodium, sodium is a group 1 cation, so it is aqueous, no exceptions. All right, I don't have the image at the ready, but refer to your handout. If the compound contains a chlorine, then it is soluble. Is barium an exception? No. So this is aqueous. That full thing, 3 points. I'm going to try one more with the time that we have left. Let's do one with a transition metal. Yeah. Okay. Here we have the reaction between iron oxide as well as sodium hydroxide. You have the steps written down already. I'm not going to rewrite them. Step number 1 says identify archetype. A, B, C, D. Leads us to A, D plus C, B. The first thing we're going to do is match ions. We're not going to crisscross. We're not going to balance. All we're doing now is matching. A ends up with D, FeOH. C ends up with B. This is sodium and oxygen. Notice that I did not automatically carry over the 2 here or the 3 here. Why? Neither one of them are polyatomic. All I have done is matched ions. Now I'm going to crisscross. I'm going to arbitrarily start with the sodium and the oxygen. Sodium is in group 1, so +1. Oxygen is in group 16, so 2 minus and plus. This is the case where we're going to have to crisscross. The 1 goes down, the 2 goes down. This becomes Na2. Oh, I'll write this a little bit better. Okay, that's crisscross. That's satisfactory to me. Then we have FeOH. OH is a polyatomic ion. It has a charge of -1. What is the charge of iron? We have no idea. It's a transition metal. We can't just look at the periodic table and tell. What do we got to do though? We got to look at what's been given. Fe2O3, we're going to reverse crisscross. The 2 gets swung up. That makes sense. Oxygen is 2 minus. The 3 gets swung up. 3 plus. This is why it's important to take a time to identify the charges. The iron, we now know, is 3 plus, and the OH is -1. This tells us we're going to crisscross and end up with FeOH3. As written, are my products correct? As written. I hear a couple no's. I see a couple heads shaking yes. To those who said no, why is it wrong as written? I need brackets around the OH. Why? Because if I left it, I'm implying there are 3 hydrogens and only 1 oxygen, which is wrong. So the bracket removes the ambiguity. Match ions, crisscross when needed. Now we're going to balance. 2 irons on the left, 1 on the right. Easy fix. Just put a 2 right there. Iron is now balanced. 3 oxygens on the left, 1 oxygen on the right. Easy fix. Put a 3 in front. Iron is balanced. Oxygen is balanced. Then we have sodium. 1 sodium on the left, and in total, 6 sodiums on the right. To balance that, we'll just put a 6 in front of the NaOH. 6 OHs on the left. And oh my God, would you look at that? 6 OHs on the right. This is a fully balanced reaction with correct products. All we're missing now are our state symbols. Obviously, I gave you the state symbols for the reactants, so let's focus on the products. You have the handout in front of you. We're going to focus with OH. If the compound contains an OH, then it is solid. Is iron an exception? No. So this is solid. Sodium, group 1 cation, is aqueous, no exceptions. And that's that right there. All right, we're wrapped up for today. That's all I'm talking about. But remember, we're continuing our discussion of reactions on Thursday. No in-class problem set, but on Friday, we do have a workshop. The priority is I want you to learn and understand the materials such that come Friday, we hit the ground running. If anyone has any questions, come talk to me afterwards. Have a good day, and I'll see you on Thursday. Yep.